Hello, I am Dr. Ajay Sharma, Department of Electronics and Communication Engineering, JIMS Engineering Management Technical Campus, Greater Noida. The subject that I teach in this semester is digital communication, and the topic that I discuss today is analysis of digital receiver. As far as the analysis of digital receiver is concerned, uh, and we always start with the basic receiver, right? The receiver sometimes called as a filter because what is the function of receiver? Is the function of receiver to give the output, and the output always comes when you remove the noise content, and for that purpose you need a filter. So receiver sometimes called as a filter also, right? So we have to start with integrate and dump filter, that is a receiver, and this is the basic receiver. When you go through the analysis of digital receiver, you always start with the basic receiver, then you able to understand next level receivers. So you always start with the basic receiver, and when you go through the book, you will find this particular integrate and dump filter, right? So we have to start with that, right? So in digital in digital communication, as we all know that we have to send the pulses, and these pulses represent 0 or 1, right? And these digital pulses have a certain voltage level, right? Particular voltage level identify or designate 1 and 0, right? So now what we consider a input digital signal, and this input digital signal is represented. If you look at the picture, look at the integrate and dump filter picture, this xt is input digital signal, this xt, and this xt is a pulse. That pulse may represent 1 or a 0, only two possibility, right? So this is the input digital signal, and that signal is to be sent from the, which is of course a pulse, digital pulse, and that xt is to be traveled through a channel, and channel always introduced a white noise, NT, and the nature of this white noise is additive. So this is xt, this is NT, and NT is additive. So this NT add into this xt. So your input digital signal is distorted by this white noise content. This is external voltage that disturb your input digital signal, and so this NT is add into this xt, right? So this xt plus NT reach at the receiver, or you may say input of the receiver, or you may say input of the filter. Filter is a part of receiver, right? So this noisy signal xt plus NT is applied to the input of integrate and dump receiver. So we have to apply this xt plus NT, right? Now, as the moment this particular pulse, where noise is also be added in that, reach at the receiver, at that moment what you have to do, you have to discharge the capacitor. Means whatever the capacitor hold a voltage, you have to discharge that, right? So the capacitor should be empty before the particular input signal reach to the receiver. So you have to sure that before the particular pulse knock the door of this receiver, this capacitor should be empty. So you have to discharge that by closing the switch S2, right? Right. Now, as this is a actually in this integrate and dump filter. Look at the name dump filter. Dump filter, integrate and dump. Dump means we have to use a dump switch S1. That's why we called it dump switch, dump filter. Integrate means this particular receiver use a integrator circuit. So the name, why this particular name of this particular is receiver, integrate and dump filter, because integrate means this there is an integrator in the circuit and there is a switch as which we called as a dump switch. That's why we call that receiver or filter as a integrate and dump filter, right? Now look at this. So this is an integrator, and all we know that if the input of the integrator is a square pulse, the output of the integrator is a triangular pulse, right? So this is the basic concept involved in the integrator. So what happened? So the integrator then integrate noisy input signal over one bit period. So what happened? What happens? This integrator then integrate noisy input signal. Noisy input signal means xt plus nt over one bit period. Over one bit period. So some voltage is developed over the capacitor, and the capacitor is start charging up to the time interval which is equal to the 1 bit period of a pulse. Then what happened? So look at the picture. This is your input. And to understand that, what we assume that there is a no noise to understand this principle, the basic concept. So what we have this is square pulse of the time t is equals to capital T having amplitude xt. Sorry, A is the amplitude of this xt, which is the pulse that reaches to the receiver. Now what happened? Integrate signal is shown in YT in figure. Now after the then what's happened? The output is YT. The output is YT, and the capacitor then start charging. And what is the time interval of charging? It is equal to the 1 bit period. And after that 0 to t, the capacitor is charged at AT by tau. A is the amplitude of xt, t is the time period of charging, and tau is the time constant of a capacitor. Every capacitor has a time constant that describes the time of capacitor to charge, right? So the integrator signal is shown in the show as YT in the figure. So for the square pulse input, the output of the integrator would be a triangular pulse as shown in figure B, right? So this is the input of the integrator, square pulse, and you get the triangular pulse at the output because of the property of the integrator circuit. So the capacitor charge up to the voltage level of AT upon tau. Now at the end of bit period, and bit period is t is equals to capital T, the magnitude of YT attain its maximum amplitude, right? So because when the capacitor charge, it start with a minimum voltage reached up to the maximum. So this AT upon tau is a maximum voltage, and that AT upon tau appear after full time period of 1 bit, right? So at the end of bit period, that is t is equals to t, the magnitude of YT attain its maximum amplitude. Hence, the value of YT is sampled at the end of bit period, right? So when this particular capacitor is fully charged, then whatever the voltage level this capacitor have, receiver take the decision on that basis, right? On that basis, if the receiver find that particular voltage level is above the threshold we already defined in receiver. So if this AT upon tau is above the threshold voltage level, then receiver declared 1 is received. And if this AT upon tau is below the threshold, then the receiver declared it is a 0, right? So it can be further proved that the signal to noise ratio is maximum at the end of the bit period. This is also be true. So S by N ratio, because we know that when the pulse that reach at the receiver contain a noise content also, so there is a noise power also in a also available in a pulse that pulse reached that pulse. So there is always some signal to noise ratio is to be attached with this pulse. Why? Because noise is mixed, noise is summed to this pulse. So the pulse that is reached to the receiver have a signal power as well as a noise power, because noise is already mixed during the transmission through a channel, right? So this pulse have some signal power as well as noise power, and that makes signal to noise ratio, right? So depending upon the value of yt means at upon tau, the decision is to be taken. The decision is to be taken, right? Then after the decision, after the decision comes on the basis of threshold, because if yt attains a voltage which is above threshold, then the receiver declared as 1 is received, and if this yt attains a voltage at upon tau which is below the threshold, then receiver declared 0 is received. After the declaration, then what happened? Then again you want capacitor is empty, because the next pulse knock the receiver door, or wait for its sampling, right? So what you want that capacitor again discharge and become empty, and before the next pulse reach at the receiver. So the dump switch is then closed momentarily to discharge the capacitor to receive the next bit. So next bit is received by this receiver when the capacitor is fully discharged, so that the decision is solely depends upon the present voltage, and it is unaffected with a previous voltage, right? So it should be necessary that the capacitor should be empty before the next pulse or next bit reach to the receiver or input of this filter. That's why the dump switch is then closed momentarily to discharge the capacitor to receive the next bit. Look at the picture again. So this is a square pulse, this is the input. In this particular example, in this picture, we assume that there is no noise in the pulse. So this is solely because of this particular A voltage, solely because of the signal power, right? And this is the output of the integrator, and on the basis of this output, which is this yt, which is at upon tau, integrator takes the decision. So therefore the integrator integrates, that is generates output which is independent of the value of previous bit. That we sure on what basis we sure that the output which is independent of the value of previous bit, because we already discharge the capacitor before the next bit come to the receiver side, right? So that's why the dump switch is necessary in this filter or in this receiver to empty the capacitor after 1 bit period, right? And again the capacitor is charged for the next bit, and again the decision comes out be on the basis of a threshold. So in that way this receiver receives bit each bit, then capacitor charged, attains a certain voltage, then receiver compare it with the threshold. If the receiver find above threshold, and then receiver declare 1, and if receiver find below the threshold, then the receiver declare 0. So this reveals that the fact that the detection in integrate and term filter is unaffected by the values of previous bits. Thank you very much.